Hello, and welcome to the Math 234 Asynchronous Review. I'm your host, Steve Dragoo. And before we get started, I want to just go over a couple of quick things about actually taking the exam. So first, the exam starts Thursday, September 23rd at 8 o'clock. You'll need to start the exam between 8 and 8:15 in order to have all of the time to take the exam. The partial credit submission will be due by 9:30. So again, the exam has to be taken at a specific time on Thursday, started between 8 and 8:15 in order to have enough time to finish all of that. There is a formula sheet for the exam, which you can find on D2L. Here I'm at our homepage. And if we just click on this assessments tab up here on the nav bar, pick exams, and then look at exam number 1, there's a formula sheet right here. You can print that off and bring it with you, or bring it with you. You don't have to go anywhere because you're going to take it from wherever your computer is. And then you can just have this on your desk to work with. It's got all kinds of nice formulas on there. I'd recommend having it. You can also find the link to the exam was right there as well. Within the assessments tab right next to the partial credit submission, which will open up at 8 o'clock, again, due by 9:30. And the exam itself is right there. All right, so here is the actual exam review we'll be doing. You can find this thing in the asynchronous lecture notes, where it'll all be completed by the time we're done with this video. Or if you're watching the recording, it's probably available right now. In fact, I know it's available right now because it gets updated live. So without further ado, find the equation of the sphere in standard form centered at the point provided with a radius of 5. So if we're looking to get the equation of a sphere, standard form is what? X squared plus y squared plus z squared equals r squared. And that's if it's centered at the origin. If it has a different center, we'll just want to subtract the x, y, and z points. So x minus -1 squared plus y minus -4 squared plus z minus +4 squared is equal to 5 squared. Where those values are all coming from that point provided. Let's maybe zoom in on this a bit as well. Right, so we can just take each of those pieces and just plug them right into the formula. The other way we could ask a question like this is, instead of providing you with a center and a sphere, we might give you some equation where you would need to complete the square in order to find the center. So that's the other way that we'll probably talk about spheres on the exam. But the main point that you're going to want to know about these equations is that we can find the center in the middle of the equation. Right, so the center of the sphere is part of the equation if we have it in standard form, like we're looking at here. And the radius is also sort of readily available from this form. That radius of 5 ends up on the right side with that 5 squared. All right. Next up, looking at projecting one vector onto another. And this is one where I've done the work out ahead of time. And I just kind of want to talk about the highlights of what we're doing when we're projecting one vector onto another. So I know we had quite a few questions about this early on in the course. So we're going to look for a decomposition of A into vectors C and D, where C is going to be parallel to some other vector, which is B, and D is going to be perpendicular to B. So that in the end, C and D added together get us A. So what that question is really saying is, I want to find one vector that is a projection of A onto B, and I want to find another vector that's the orthogonal component of A in the direction of B. So I've done my best to color code this and make this thing kind of readable as we go through it. But if I just kind of highlight some of those pieces, we're starting with that vector A, which is in blue, and I want to project it onto vector B, which is in gray. And it's gray because it's sort of like the background, because it's just going to determine the direction that I want to go in, and I only want to pick out sort of the components of A that are in directions specifically related to B. So if I want the projection of A onto B, which that's written over here, that's going to be the yellow vector that I've drawn in. So I take some line that is perpendicular to B and draw it so that it connects to the tip of vector A, and then I've got that intersection with B, and that's as far as my projection should go up B, right? It's the piece of the vector A that goes in the B direction. So when we say we're looking for the projection of A onto B, that's what we're after. And then there's a formula that's there. It's the dot product of A and B over the magnitude of B, and then we're going to multiply that into the unit vector in the direction of B. I think that's the easiest way to kind of remember what the formula is that it's a component of A, some numerical scalar component of A in the direction of B, and then I just multiply that into the unit vector in the direction of B, which is what that whole formula comes out to. I believe that's also on the formula sheet that you get for this exam. So it's not something that you need to have committed to memory, which is nice, at least not for the exam. But then, we can actually take that dot product, get ourselves a number over here, and I ended up writing that out as just some scalar multiple of B, which is this line here, 57 over 105 times the vector B that we were given in the original part of the question. So then once we have our projection of A into the direction of B, so we just have that component of A that's parallel to B, I also want to come up with a component of A that's perpendicular to B. And if C and D add together to get A, that means that that orthogonal vector, the one in magenta, is just going to be the difference between A and C. So since I've already found C and I was given A, I can just take the difference to get that orthogonal vector. So the idea behind all this projection stuff is that normally when we talk about breaking a vector down into components, we break it down into X and Y components, or X, Y, and Z components if we're in 3 space. You'll notice this projection I just did in the 2D plane because it was going to be easier to illustrate it that way. But normally we talk about a vector in those 2 or 3 directions that are perpendicular to one another. But there's no reason we had to pick specifically X and Y as the directions that we use to break apart our vector. We could do any 2 perpendicular directions as long as we know what they are. So that's basically what we did here. So sort of instead of expressing A in terms of an X and a Y component, I want to express A in terms of a B component and a perpendicular to B component. But I don't need to drag on that too much. Let's move on to the next one. Okay, so we're going to look at the cross product between A and B, but instead of being given vectors A and B, we'll instead get the magnitude of A, the magnitude of B, and the angle that's in between those 2 vectors, and then ask to find the magnitude of the cross product, which we have a formula for this, which says that the magnitude of the cross product of 2 vectors is equal to the magnitude of each individual vector multiplied together, and then multiply that by the sine of the angle that's in between them. Not to be confused with the dot product, which is slightly different. It's a dot b is equal to the magnitude of a times the magnitude of b times cosine of theta, right? So we had two different formulas that relate the dot product and the cross product to the angle that's in between a couple vectors. One is sine theta, the other is cosine theta, and we're looking at the cross product, so we want the one that's sine theta. Which means we should just be able to plug all this stuff in and get ourselves an answer. We know that the magnitude of A is 4, magnitude of B is 2, and we're going to want the sine of pi over 3. The sine of pi over 3 is root 3 over 2. So in the end, I think this works out to 4 square root of 3. Right, 4 times 2 times root 3 over 2. Yeah, so I'm just going to the unit circle to get that sine value. So if it's been a while since you looked at the unit circle, might be worth reviewing that too. At least like the first quadrant stuff. We're probably not going to get too far outside the first quadrant, I wouldn't imagine. All right, let's next take a look at another problem out of the cross product section, but this one's going to ask us to find an area of a triangle. So given points A, B, and C, which are listed over there, we want to find the area of that triangle. Notice I've kind of sketched a spot over there on the right. So let's pretend like this is A, this is B, and then this is C. I've just done a two-dimensional sketch, but these are points in 3 space somewhere. But I think we can get the idea just from the two-dimensional illustration. So what is it that we're gonna need? I'll want any 2 vectors. I think I'm gonna choose A, B, and A, C. But you could pick any 3, and it ends up just being the magnitude of a cross product. So any 2 vectors that will connect 2 of these points, all 3 of these points together, should work for this area of a triangle. But A, B should be the vector. Let's see, I've got -6 minus -3, which is -3. Then I've got 3 minus 1 is 2. 3 minus 1 is 2. And then I've got -2 minus -2 is 0. And you know what? Let's at least write that out once. I've got -6 minus -3. I've got 3 minus 1. And I've got -2 minus -2. Which is the vector -3, 2, 0. I'll also look at the vector AC, which is -5 minus -3, 1 minus 1, and -2 minus -2. So that comes out to -2, 0, 0. Probably not going to write out those steps on every problem, but at least if it's on there once, I'll feel a little better about what I'm doing. So I've got my 2 vectors. Now I need a cross product. So I want AB cross AC, which is I, J, K, -3, -2, 0, and -2, 0, 0. And with this particular determinant, it doesn't look too bad to calculate. Looks like if I calculate either the I or the J components, I'm going to get 0, since that K column is 0 all the way down. So first 2 components, I definitely get 0. And then for the third component, I'm going to get 3 times 0, which is 0, minus -2 times -2. Whoop, hold on a second. Realized I made a mistake when writing down my vectors. My first vector, AB, was -3, +2, 0. So, well, good thing I caught that. Okay, so -3, +2, 0. I don't think I'd done any work with it yet, so we're not in too bad a shape just yet. So 0, 0, and then I had 0 minus -4. Right, 2 times -2 would be -4. So I've got the vector 0, 0, 4. Finally, I want the area of the triangle, which should be 1/2 of the magnitude of that cross product, AB cross AC, which is gonna be 1/2 times the square root of 0 squared plus 0 squared plus 4 squared. So that'll be the square root of 16, which is 4. Half of that is 2. Maybe I don't want to run away from that too fast. For anyone actively paying attention, instead just glance ahead real quick. Okay, then let's move on to problem 4. This one's almost just a conceptual problem, but I thought it was worth throwing in here, just because, some concepts are good to look at. So I want to find a non-zero vector that's normal to the plane provided. So if we just kind of multiply that thing all the way out, I've got z minus 5x plus 15 equals -16 plus 4y. And then reorganize some of these pieces. I've got -5x minus 4y plus z. And let's bring everything onto one side. Add the 16 over, that'll be plus 31 equals 0. And then start picking out the pieces I'm interested in. Which are going to be the coefficients on x, y, and z. So my normal vector n should be the vector -5, -4, and +1. So the idea here is that if I have the equation of a plane in general form, which is where I just list out the x, the y, and the z pieces, so that there's a term for each linear variable x, y, and z, and then some constant term. The normal vector is just baked into the equation. That if I just grab the coefficients off of the variables in the equation of a plane, I get the normal vector. Keep in mind that the normal vector is perpendicular or orthogonal to that plane, which is another concept that probably is going to come up. So like, what is a normal vector? So if, for example, you were asked if I have a vector that's parallel to the normal vector, then that vector is in the plane or something like that. But that would be a false statement, right? Because if I am parallel to the normal vector, that means that I'm still perpendicular to the plane. Right, so again, normal vector, perpendicular or orthogonal to the plane. I guess while I'm on the subject, talking about all those words, orthogonal is, just the 3D way of saying perpendicular. There's a slightly more robust definition to it than that, but essentially it's just perpendicular, but in 3 dimensions. Can I repeat that statement about normal vectors? Yes. So if I have another vector that is parallel to the normal vector, then that other vector is perpendicular to the plane. It will not be parallel to the plane or in the plane. Right, or say I have a line that's parallel to the normal vector. That line does not lie in the plane itself because it's going to be orthogonal to the plane. So again, the big idea is just that parallel vector or normal vectors are not parallel to the plane. They're perpendicular to the plane. But okay. Speaking of planes, I think we've got some more stuff to talk about. Finding the distance between the plane given by that equation and the line given by that other parametric equation. Oh, that's it. Just calculate the distance. Sounded like I was going to say more there, but then I didn't. So again, I've kind of worked out ahead so that I have a sketch prepared so I can kind of explain what it is that we're about to do. And if we're looking to get the distance between a plane and a line, then probably that means it's just going to be the same as the distance between some point and the plane. Because I can just pick any point that's on the line and calculate the distance to the plane. Also, this is probably going to assume that, this plane or the line is somehow parallel to the plane so that it doesn't ever intersect the plane. Because if it ever intersected the plane and we just said, find the distance, then the distance would be 0 because, well, an intersection would be a distance of 0. So we've got some line that's parallel to the plane provided, and we're just going to try to find the distance between the plane and the line. But again, rather than trying to do that directly, I would just want to get the distance between the plane and any point on the line and get that distance, because that's just a method that we already have. So let's do this thing. If I were to go through and start finding some stuff, based on the previous question, we already know what that normal vector should be. It's the vector 1, 3, 2, right? I'm pulling that from 1, 3, 2 right up there. I can also get a point on the line pretty easily because it's a parametric line. I can just pick out the point. It's here, here, and here. So Q. Actually, where do I want to put this? I'm going to need to work down below here. So maybe I've got space right here. Q will be the point. -1, -2, -1. And I get that if t is equal to 0. That's where I came up with the point. I could pick any value I want for t, really, and come up with a point that will work. But t equals 0 seems like the easiest one. Plus, it's right in there. So the next thing I'm going to end up wanting is some point that lies in the plane, right? So I found Q, which in this case is a point on the line. Now I'm going to want a point on the plane. And the idea behind what we're doing is that if I get a vector that connects any point in the plane to any point on the line, and then project that vector onto the normal vector, I will get the shortest distance between the plane and the line, sort of based on that sketch that I have right here, right? So we've got our line that's going to run parallel to our plane. So the shortest distance is a straight line, which means I'm going to want the normal vector. And then again, the way to do that is not to find that point on the line directly, because that seems hard, but instead just take any vector that connects the plane to the line and project it onto the normal vector. Yeah, and so there's a question in the chat. It says, is this the theorem where we have P0 and P1? And if that's the case, which one is which? Yes, this is that theorem where we're just going to, make a vector that connects 2 points. And it does not matter which one is P0 and which one is P1. I could have my vector go from the line to the plane or from the plane to the line. It isn't going to end up mattering because the only difference in the math between those two problems is that one answer will come out negative while the other answer comes out positive. And since we're just looking for the distance between the planes, I care about the absolute value anyway. So if in the end I get a negative number, I'm just going to take the absolute value and say that's my distance. So I don't really care if I have to go forward or backward to get that line. Or sorry, to get that distance. I don't care if I'm going forward or backward to get the distance. So next up, I need a point for P. And here's where I know we get quite a lot of questions on this. So I need any point that's in the plane. And my plane's equation is x plus 3y plus 2z equals negative 23. So how do I pick a point that's there? And the explanation that we usually give is, yeah, just like pick any point, or I don't know, pick some variables and make them 0 and then see what's left over. And while that is what we're going to do, that answer kind of sucks. So let's see if I can get a slightly better answer to that question. So we have the equation of our plane, and we just have one equation, but it has 3 variables in it, right? X, Y, and Z. And it's the only equation that we have. So again, one equation with 3 variables. And sort of generally speaking, we can use one equation to solve for one variable. So if we wanted to like actually come up with a specific point, we would need 2 more equations. So I have a system of 3 equations with 3 variables, means that I can solve for a specific answer, but I don't have a system of 3 equations. I have a system of 1 equation, that being my plane. Which means of the 3 variables, I can only really solve for 1, which means 2 of my 3 variables are free variables. So I can choose whatever I want for 2 of the variables, and then the third one would be determined based on my choice. There are a couple of other problems where it seems like we're looking for the intersection of 2 planes, in which case I have a system of 2 equations with 3 unknowns. And in that case, with 2 equations and 3 unknowns, I still have 1 more variable than I have number of equations. So I have 1 free variable again in that setup, where I can just pick anything I want for 1 variable, and then my choice there is going to determine the other 2. Because once I like pick a number for the first variable, then I have a system of 2 equations with 2 unknowns, and I can solve that. Coming back to the problem at hand, I have a system of 1 equation, so I'm going to pick 2 variables to be whatever I want, and then I'll have 1 equation with 1 unknown, and I can solve for it. And that's the long-winded version of why we say, yeah, just like pick a couple things to be 0 and see what you get. But it goes back to systems of equations in algebra, is sort of why we get to decide to do what we want to. So with that preamble out of the way, let's look at what we have. X plus 3y plus 2z equals negative 23. Negative 23 is not divisible by 2 or 3. So I'm going to set both y and z to be 0 because I just don't want to deal with those extra coefficients. So again, I got to make 2 choices because I only have 1 equation with 3 unknowns. And my choice is to pick y and z to be 0. If I do that, I'm left with just the equation x equals negative 23. And that's enough to get me started on finding everything else I'm going to want. Cool beans. All right. So now that I have my points, and again, both choices of the points were pretty arbitrary. I just went with what I thought would make the math the easiest, which usually means playing in 0 as often as possible. So 0 for t, 0 for y, 0 for z. And I want now a vector that's going to connect those 2 points. So I wrote it down as finding PQ. So PQ, if I go in that direction, it's going to be, what do we get over here? So it's Q minus P. So -1 minus -23 is positive 22, -2, -1. Cool. So now I've got myself a vector. The work from here is to just project this guy onto the normal vector, right? Because in the end, the thing that I want is C. So if I just look at the absolute value of C, or the magnitude of C, which is the distance, that means I just want the component of PQ that is in the direction of N. Right, so I don't even need the full projection. I only want the component part, which means I don't need to do the part where I have to like multiply by the unit vector. And let me just grab our normal vector that's up there, slide it down a little bit so that it's still on screen. So this component ought to be the dot product of 22, -2, -1 with that normal vector 1, 3, 2, divided by the magnitude of our normal vector, which is 1 squared plus 3 squared plus 2 squared. And we would get a number out on the other side. The dot product at least comes out really, oh no, didn't come out quite as nice as I was hoping for, but that's fine. What do we have over here? 22 minus 6 minus 2 divided by the square root of 1 plus 9 plus 4 is 14, which is 14 over the square root of 14. 22 minus 8 is 14, last I checked. I'm not always very good with numbers, so shout me out in the comments if I ever get a number wrong. But yeah, this looks like square root of 14. If I simplified that. That last step is optional. I don't think you need to simplify 14 over root 14, but I'm going to because I know how, I guess. Yeah. Right, and so again, that was our distance because we just needed the magnitude of C. Technically, I should have some absolute values in here too, but it ended up coming out positive, so I didn't need them. So I guess we'll say I knew it was going to be positive before I started. Can I scroll up a little, please? Yeah, I can do you one better, I think, and zoom out a little bit so that we can get the whole problem on the screen at once. I'll let it sit there for just a second. Because in a moment, I think we're about to start looking at section 12.6, which are all those quadratic surfaces. So, oh yeah. And hopefully I'll be able to shed a little bit of light or provide an easy way to try to remember what matches to what. I know there's that flow chart that I think someone actually made that flow chart and put it on Piazza, which was a great help. So if you made that, kudos to you. Nice work. Or if you found it, then hey, thanks for finding it. But on down to the next problem. Yeah, here it is. Okay. So I've copied a page out of the book, which I thought would be helpful. And It's just on page 854, and it's just a quick explanation of for the most part, the 6 basic quadratic shapes that we look at. Everything but the cylinder is listed here. And that is helpful. It's also in the course notes, or again, you can look at that flow chart that somebody had posted. But also, I tried my own hand at coming up with a set of equations. It's somewhat easy to remember, I hope. So I broke things down into sort of 3 basic shapes to talk about what they're going to look like. I sort of excluded cylinders and spheres because I think those tend to be the easiest ones to look at. By spheres, I mean ellipsoids, whatever. So paraboloids, hyperboloids, and then cones. And my method for remembering which one is which, nope, almost, is I first separate it into some kind of a parabolic equation if I have one, or some quadratic looking equation if I have one. Parabolic, quadratic is everything. Forget I said quadratic. Parabolic shapes versus non-parabolic shapes. Starting with the parabolic shapes, those are usually pretty easy to identify because the hallmark of a parabolic shape is a linear term mixed with a square term. So a linear term and a quadratic term mixed together is going to give us some sort of parabolic shape. Meaning anytime we have a linear term in our quadratic equation, we're going to end up with a parabolic shape. So I started by separating out into the linear options, and then there are 2 categories within the parabolic shapes. There's an elliptic paraboloid and a hyperbolic paraboloid. Elliptic is if the leftover equation looks like an ellipse or a circle, which means x squared plus y squared, or it's hyperbolic if it looks like a hyperbolic equation. The difference between an elliptical equation and a hyperbolic equation is that an ellipse or a circle is going to be x squared plus y squared, while a hyperbolic equation is going to be x squared minus y squared. So that's just the difference between the negatives there. Then if I have all three of my terms are square terms, so x, y, and z are all squared, then I'm probably looking at some kind of a hyperboloid. And we'll also fudge and say that a cone is a hyperboloid, kind of, because it's kind of going to help out with the explanation. And then the way that I like to set up these equations is I move everything onto a side so that it can be positive. So if you'll notice with the other 3 equations that are, I guess, the blue and yellow ones, I've got every term is positive, which means if I have a negative term, I'm just going to add it to be over on the other side. And then I can say that my hyperboloids, which are the crazy looking things, if I have just one square term on the side that contains the constant, then it's a hyperboloid of 1 sheet. And if I have 2 terms on the side that contains the constant, it is going to be a hyperboloid of 2 sheets. And then finally, if I do not have a constant, meaning my constant is 0, I'm going to end up with a cone instead. So 1 term is 1 sheet, 2 terms is 2 sheets, and then a 0 constant term is going to be a cone. But if we look just back up at these pictures real quick, when I said earlier that a cone is kind of going to be, we're going to fudge it a little bit and call it a hyperboloid as well. If we think about what role our constant is playing in those 3 equations or those 3 diagrams on the right, these 3 guys over here, the constant is just going to determine what this shape looks like at the origin. Outside of the origin, they kind of follow the same basic behavior of having circular cross sections that are parallel to the XY plane. It's just a matter of, what happens in the middle. Because outside of that, these 3 equations all kind of look fairly similar. The cone, I think, is the easiest one to sort of visualize because, well, it's two cones. They come together right at the origin at some point. And if I'm adding a constant term into that cone, it's going to make the whole thing get wider about the base. And if that cone gets wider about the base, it becomes a hyperboloid of one sheet, where instead of having a single point of intersection at the origin, it's going to have a circular intersection that's in the XY plane. And if I start subtracting a constant from that cone, so go the other way, I'm going to be cutting out a section in the middle as this thing sort of collapses in on itself, which is what then separates the hyperboloid into two separate sheets, one that's like part of the top cone and one that's part of the bottom cone. And so maybe there's another explanation that makes sense, or maybe you're just as confused as when we started this whole shindig. And well, I guess at least I tried. But enough of me just rambling on about all that. Let's actually go try and solve some of this stuff. So in that first equation, we have a surface given by, and I'm going to ignore constants or ignore coefficients, x squared plus z squared equals 1 plus y squared. So I think that this thing is a hyperboloid of one sheet. Hyperboloid of one sheet. Right, so if I go with the explanation that I gave earlier, I have just the one term. Notice all my terms are positive, and I have just one term over with that constant number on the right. So it's a hyperboloid of one sheet. Looking at the second one down, x squared plus y squared equals 1 minus z squared. If I add that z squared back over to the left side, I will have 3 positive terms equals 1, which must be an ellipsoid. Because it looks pretty similar to an equation for a sphere, this with an extra coefficient in it. How the heck do you spell ellipsoid? Ellipsoid? Probably close enough. Next up, we've got a surface. X squared is equal to y squared plus z squared. All 3 terms are positive. All 3 terms are square terms. And my constant term is 0. So this thing must be a cone. Since again, constant was 0. Compare that to the next one down, x squared minus y squared minus z squared equals 1. Any which way we look at it, that thing should come out to be a hyperboloid of 2 sheets. Hyperboloid, 2 sheets. Can you explain the fourth one? Yes, I think so. Okay, so what I'm doing with that fourth one, okay, how do I want to mark this thing? I haven't used red yet. Let's use red. So marking this one down here. So I'm going to take x squared and leave it on the side that it's on, but I'm going to just add everything around to make it so that all my terms are positive. This is x squared equals 1 plus y squared over 4 plus z squared over 4. So I think that if I come back down to the method that I just talked about, it must be a hyperboloid of 2 sheets because I've got the 2 square terms on the side with the constant. Was my thought there. Alternatively, if we just look at the equation as it stands, I think it almost directly matches the one that's given by the textbook over here. Negative x squared, negative y squared, positive z squared equals 1. And I don't care which of my variables is positive and negative, just as long as 2 negative with 1 positive and a positive constant on the other side. But again, I sort of like my method. One of the reasons I like my method is that the first step is sort of simple. It's just make every term positive and then start looking at what you have. So there's less of that like, well, how many negative terms versus how many positive terms, because that can switch based on which side of the equal sign it's on. Also, what do you do with the constant, positive or negative or whatever? And then with my system, everything can just be positive. I can work through it from there. Quick question, why is the third one a cone? So yeah, that is an excellent question that I'm going to read out loud so that it also gets into the recording. Okay, so why is part C, or the third part, why is that one a cone? Because I think that if you move the y squared and the z squared terms over to the left, you'd end up with one positive and two negative terms, which is sort of indicative of a hyperboloid of two sheets. Great question. And here's where there is a bit of a trick to some of the methods that we use to like describe these equations. Because while you can say, yeah, just move the y squared and the z squared to the left side, and I have one positive and two negative terms, I could also move the x squared to the right side, and then I'm looking at two positive and one negative terms. Nah, I used the wrong plural there, but hey, whatever. So what gives? And that's where I would kind of come back to that explanation I was giving a couple minutes ago about how the hyperboloids of both one and two sheets are really connected to that idea of a cone, right? That's the one sheet is just a cone that's been expanded at its center. A hyperbole, or taking your two cones and like compress them down vertically, like smash them together so that they start running into each other in the middle. And a hyperboloid of two sheets is if you have two cones, but then you separate them apart in the middle. So that cones and hyperboloids end up being really similar shapes. So that the reason why with that one that's a cone, where I could write it so that it shows up either as a hyperboloid of one sheet or as a hyperboloid of two sheets, based strictly on how many negative versus how many positive terms we have, that's a big reason why I like saying just make all the terms positive and then look at what you have. Because if you make all the terms positive, then you probably start focusing on, hey, where is the constant term? And in the third example, where we're looking at a cone, we find that there is no constant term, or that the constant term is zero, meaning we know from that it must be a cone, because cones have a zero constant term, whereas the hyperboloids of one or two sheets have some non-zero constant term added in. So I know for certain it's not one of the hyperboloid shapes because the constant term is zero. Cool. So hopefully that explanation makes sense. Looks like it's going over somewhat well in the live rendition of my Calc 3 review. We'll see what it looks like in the recording. Post on Piazza if you've got more questions. Right. So let's take a look at another one. X squared plus y squared plus z squared equals 1. This one's one of the easier ones. It's the unit sphere. Which of the options provided is an ellipsoid? So it's sort of like how a square is a rectangle and a circle is an ellipse. A sphere is an ellipsoid. So all three terms are positive and all three terms are square. We got ourselves an ellipsoid. And if we look at that bottom one, x squared plus z squared equals y squared. Notice again, there is no constant term. So we are once again looking at a cone. Because, yep, our constant term is 0. So one thing worth talking about, just so we can get an idea of what's going on with these cones, because there is a bit of a system to how it all works, right? Because there's one side of the equal sign that has one positive term, and the other side of the equal sign has two positive terms, And that will tell us something about the shape of the cone. Because it's always going to be the term that's by itself. So in the third equation, it's x is by itself. In the sixth equation, it's y that's by itself. That lonesome term, is the one that's going to tell us which axis the cone expands on. So the third example will expand along the x-axis. The sixth example expands along the y-axis. And then the given example that's in the textbook, if we look up here in that upper right shape at the cone, that one expands along the z-axis because it's z is the lone term with x and y together on the other side. So, the more you know. Since we don't really need to end up doing any math with these shapes, mostly we're looking at this section so that when we do integration in 3-space, we can have a little bit better idea, or at least we can come up with some kind of an image of what's happening when we want to talk about 3-dimensional shapes. We're almost never going to get into like sketching out specific shapes. It's just, do you know what the equation of an ellipsoid looks like? Or if I have, an elliptic paraboloid, then does that thing have a minimum value or a maximum value somewhere? So if you remember your calculus from, a couple of years ago, or maybe a year ago, whenever you took Calc 1, we're going to be finding max and mins again. It's going to be a little while before we get there, but it is coming. Okay, let's take a look at the next problem down the list. Let's see, how far along are we? We're a little over halfway through, I think. Oh, we must be because we're into homework 6 already. So it's just 6 and 8 are left. We're in chapter 13. Enough rambling. Let's just solve this thing. Solve the initial value problem. The derivative vector r is given right there, and we're also told that r evaluated at 1 is equal to some point. So if we want to get r, and we're going to play a little bit fast and loose with the notation here, because I think it helps us make some sense out of it, even if it isn't like the most technically correct version of the notation. So if I have the derivative vector and I want to get the initial vector, I should just integrate each term. So let's integrate 10t dt. And let's add some color to this. It looks kind of boring and it's got no color in it. I also want to integrate 5 dt, and we'll integrate 12 root t dt. Right, well, that came from here, and it came from here, and it came from here, and it's a good thing I went up to highlight this stuff because I noticed a mistake. Let's slide to the right. Okay, sorry. This should have been 10t plus 4. Nope. There's already a question in the chat about it. Yeah, no, we did not want to ignore that 4. That was just me having it's kind of a mental typo right there. Okay, yep, definitely want to include the whole thing. So that's why it helps to reread the problem. So if we do that, what do we end up getting? This will be 5t squared plus 4t. Where do I want to add in let's add in c as a separate vector. So 5t squared plus 4t, we've got 5t here in the middle, and we've got 12 square root of t, that's t to the 1/2. So I think the thing integrates to 8t to the 3/2. And then to that, we're going to need to add a C vector. Right, so sort of, back in Calc 1, whenever you take an indefinite integral, you have to add a constant term at the end. We just took 3 separate integrals, so we're going to need to add 3 separate constant terms, but I'm just writing it off to the right as a single constant vector that I'm going to need to add to this thing. And then that'll let us solve for this here shindig. So R of 1, which we know to be the vector 9, 10, 12, 9, 10, 12. That thing has got to be equal to whatever we get when we plug in 1 for t, which should be 5 plus 4, 5, and 8. Plus that C vector, which I'm going to actually write out explicitly now, C1, C2, C3. Yeah. So now all I want to do is solve for each of those C values. So if I just subtract that thing over to the other side, 5 plus 4 is 9, but then 9 minus 9 is 0. 10 minus 5 is 5. And 12 minus 8 is 4. So that C vector, C vector, not G. That C vector is going to be 0, 5, 4. So if I wanted to actually write this thing all the way out, and I'm going to use technology to my advantage here. I'm just going to hit the copy button up there and say that R of t is equal to, okay, don't fail me now. Okay, I really hope I hit my mute button before I sneezed right there. Many apologies if I didn't, because I'm sure that was loud. So yeah, really hope I hit that. So right, I copied and pasted my R of t value from earlier, and all I want to do now is just add in those constant values. I'll make ourselves a little bit of space in each spot to add them all in. Oop, come on, let's grab the whole thing. The whole thing, I said. Okay, cool. So adding in our C values, I got 0 on the X component, I got 5 on the Y component, I got 4 on the Z component. Isn't it supposed to be 18 instead of 8? I don't know. Let's check it out. So I wanted to integrate 12t to the 1/2, right? So integrating t to the 1/2, I want to bring my power up to 3/2, right? Because I'm going to add 1 to it, divide by the new power, divide by 3/2. That means multiply by 2/3. And 12 times 2/3 is 4 times 2, which is 8. So pretty sure 8 is right. Okay, cool. And the chat agrees with me now. So I'm going to assume that my numbers were correct there. But once again, I'm not very good with numbers. So good on you for double checking. You never know when I'm going to get one wrong. Hopefully not in the exam review. But hey, I mean, you never know. Okay, on to homework 8, which I've based on all the Piazza responses. This is everyone's favorite. So let's just get to it. So at what points does the curve R of t intersect the paraboloid z equals whatever? So this is probably a good time for me to plug my notes that exist on Piazza. So the asynchronous course notes should link you to this OneNote document where I've got all my notes kind of gathered in one spot. And if you watched the videos on my asynchronous videos on 13.1 and 13.3, you probably found that they were kind of short and lacking in examples. So as the semester goes on, it's kind of my goal to add to those notes some more. So if you check the notes specifically for sections 13.1 and 13.3, there are extra examples added to the written notes that aren't covered in the videos. And I think this is one of the problems that I expand on in the written notes, or a problem like this. I know that there's at least like a picture of why that curve is a helix and what it looks like if it's going to intersect with some other shape. But again, you may want to check the written notes for extra examples. Rufus, calm down, buddy. All right. I have a dog. He's freaking out right now. Yeah. Okay. So what have we got here? We want to get the intersection of that there helix. Is it a helix? No, it's just a curve with a paraboloid. There was another question where I looked at a helix and I got confused. So given that we have a parametric equation here, we have equations for x, for y, and for z. So the coefficient on I is the x part. The coefficient on k is the z part. The coefficient on j would be the y part, but there is no j part, which means y is going to be 0, which will kind of make things look a little nice for us. That means there's one extra piece we don't have to deal with. So I'm going to take this equation and plug stuff into it. I've got z equals x squared plus 5y squared. Z, I know, is 5t minus t squared. On the other side, I've got x squared, and I know that x is 7t. And then I have plus 5y squared. But again, y is 0. So this thing just looks like plus 5 times 0 squared. All right, and now I have just one equation with one unknown, that being t, so I should probably solve for it. Foiling some stuff out, what do we get? 5t minus t squared is equal to 49 t squared plus 0. If I start grouping some stuff, I'm going to have to add t squared over, so this will give me 50 t squared minus 5t. And since this thing is equal to 0, I don't want to divide by t because that'll kind of mess me up. So instead, I'm going to factor out everything I can. Call this thing 5t times 10t minus 1 equals 0. Doing so, I should probably get a couple different options for t. T equals 0 or t equals 1/10. Right, from those two individual pieces, t equals 0 or t equals 1/10. Highlight those guys in green. So my goal was to just find where the curve intersected the paraboloid, which means I'm looking for points. And I now have the t values that can tell me what those points are, which means I want to find r of 0, r of 0, and I want to find r of 1/10. So r of 0, what did we have? 7t was our x value. These are points, so I'm going to write them out as points rather than as vectors. So plugging in 0, I think I'm just going to get 0, 0, 0. Right? If I come back up and check that equation, I'll write it down here again. So we have it. R of t is equal to blah. It's equal to 7t 0 and 5t minus t squared. There we go. Now we've got our equation where we can see it. So plugging in 0, 0, 0, and then 0 minus 0. Cool. 0, 0, 0. On to the other piece. Plugging in 1/10. I should get 7 over 10 for x. I'm going to get 0 for y. And then I'm going to get 5 over 10 minus 1 over 100. And I could simplify that if I wanted to, but I kind of don't want to. So let's just leave it at that. You've got a calculator that can do that anyway. How did you get 0 and 1/10? Good question. So those pieces are coming from 5t equals 0 and from 10t minus 1 equals 0. All right, so if we recall some of our algebra skills, there's the zero product principle, which states that anytime I multiply two things together and I get 0 as a result, that means that one and or both of those factors that I multiplied together must be equal to 0. It's the only way to get that to happen. And it only applies when we're equal to 0, lest someone try to apply that when it's like equal to 1 or something. Be a little careful with that. Zero product principle only applies when the product is 0. Sorry. It's been a long day. But yeah, 0 and 1/10 from those two pieces. Oh boy, everybody's favorite, parameterizations. So earlier I was, talking up my notes about how, hey, there's some extra examples in there. Most of the examples I added to 13.1 are all about a review of parameterization. Because it looked like, based on some of the comments in Piazza, it seemed like that might be a good idea. So I've updated that to include some new notes. So we've got two things that we want to parameterize: a cylinder and just some other surface, where I'm not explicitly saying what it is because it looks complicated. I think it's a paraboloid, actually. In fact, probably an elliptic paraboloid, but whatever, getting ahead of myself. So yeah, we got those two things. Let's figure out what comes next. So parameterizing these equations. And I know one of the super fun questions is sometimes when we have two square terms that we had together, we parameterize it with sine and cosine. And other times when we have two squares that we had them together, we don't use sine and cosine. What gives? How do you know when to use one or the other? Let's see if I put more notes in here. I did. Cool. We'll come to that in a second. But the simple answer is you don't always know with absolute certainty when to use one or the other, but a really good and pretty reliable, and hopefully still reliable through the rest of the course, way of deciding when to use sine and cosine and when to use a different parameterization is by looking at the other side of the equal sign. In our case, our two square terms added together is equal to a constant number, which means that it's looking like the equation of a circle. Anytime it's equal to a constant number, we probably want to use sine and cosine as our parameterization. So this is looking good for sine and cosine. But if we had something like x squared plus y squared equals 81z, then we're probably going to want to use something else. Probably something else. And that something else is probably going to be either x equals t or y equals t. Depends on what our other equation is. So the big difference between the two, as you might have noticed, is that in one case, we're equal to a constant number, and in the other case, it's equal to some variable. If I've got another variable in there, sine and cosine doesn't always work as well. But anytime it's like x squared plus y squared equals constant number, more than likely sine and cosine is going to be the parameterization that we want, because we're looking to go around a circle. So since this thing is x squared plus y squared equals 81, I am probably going to want to use x equals 9 cosine t and y equals 9 sine t. Now I can switch those up if I want to. I could have x be sine and y be cosine. It doesn't actually matter. Sort of the traditional way that we usually do it, if we go back to like polar coordinates or the unit circle, usually x is cosine and y is sine. But that definitely gets funky when we start adding z in, because then like, what do you do if it's y and z or x and z, right? Those are the other two combinations. And short story is that it doesn't really matter which one we pick to be sine and cosine. Most of the time, it doesn't matter. In fact, pretty much anything we look at, it won't matter. So we've got what parameterization we think is going to look good. So notice that it's 9 cosine and 9 sine, because I took the square root of 81, because 81 is going to be my r squared term. So r cosine and r sine is what I went with. There's a more robust explanation in the notes if you want to go check that out, where I deal with like parameterizing an ellipse instead of a nice circular shape. But ours is a circle, so let's just take that and run with it. So we've got our x and our y, and then we want to say that z is equal to x times y, or 2x times y, 2xy, now which means that it's 2 times 9 cosine times 9 sine. 9 sine. I feel like that's rhyming just a bit too much. And then we could like simplify that if we wanted to, or we could just leave it in its factored form. Personally, I'm preferable to leaving it in its factored form. It'll probably be easier to work with it later if we need to. So it's great and all when you just pick the right parameterization right from the beginning and everything works out just fine. But what do you do if that doesn't happen? Well, let's scroll down and take a look. And here, I've got way too much space between this and the next example. Oh boy, here it goes. All right. So this is one of the notes that's, or one of the examples that I put in my notes that I just decided to copy and paste over here, of actually experimenting with choosing some different values for t and seeing what happens and why maybe some choices are going to be better than others when we're looking at a parameterization. So for starters, I've got the paraboloid y equals 13x squared plus 4z squared and a parabolic cylinder, x equals z squared. And we're going to try some parameterization here. So notice, harkening back to the example I just talked about, where I had x squared plus y squared equals a constant, and I wanted to use sine and cosine for x and y. This time, I have x squared plus z squared equals y. So I don't want to try sine and cosine this time, at least not right away. So again, since it's equal to a variable, I'm not going to try sine and cosine for x and z. Instead, I'll just try some other stuff. And it seems like almost every example on WebWork always works out to x being t. So I'm going to try that first, see what happens. So if I do that, I'm just trying x equals t because it seems like the easiest parameterization to work with. I run into a bit of a problem right away because I end up with the equation t equals z squared. So notice I'm just going to this equation right here, x equals z squared, plugging in t for x, and end up getting that z has got to be plus or minus the square root of t. It's undesirable for a few reasons. Just defining it as the square root of a parameter right away, not great. But the thing I'm really concerned about is that plus or minus right there. Right, I really don't want to have a plus or minus in my parameterization because then I have to have some sort of piecewise function for a parameterization, and the whole idea behind creating a parameterization is that once I have it, it's easy to work with. I know that the journey to getting there isn't always easy, but once it's done, it should be something easy. And having a plus or minus involved isn't particularly easy. So that failed. I don't really like where that went. Let's try something different. So instead of x being t, let's try y equals t. That's now the second equation. There's only one place to plug in for y. So I did that in the top equation. I get 13x squared plus 4z squared. I still have x equals z squared. I could substitute that in and have like z to the fourth plus z squared equals t, and then somehow I've got to turn that into an equation for z equals something with t. Yeah, that looks hard, and I don't want to do that. So I'm going to try something else because that didn't seem to work. So the other option, let's try z equals t. Going about it that way, I get just x equals t squared. So now I've got two particularly nice looking equations, z equals t, x equals t squared. I notice I don't run into the plus or minus this time because I didn't need to take a square root. And now that I have an equation for both x and for z, I can plug those into that top equation and get an equation for y that only depends on t. So 13t to the fourth plus 4t squared, or t squared squared is where I got t to the fourth. And that was way nicer than the other two. So that's the parameterization I would stick with. After trying three of them, there was one that was easy and two that were not easy. So don't go with the ones that are not easy, since the idea is it's supposed to come out to something nice to work with. Let's undo that highlighter right there. So let's also undo this one. All right, one more crack at parameterization. And not only that, but we're finding arc length to go with it. And over here, looks like I've put a trig identity that's probably going to be helpful. At least I don't know of any other reason why I've written it down right there. So let's give it a crack, see what happens. So we want to get the arc length of this thing, right? The length of a curve, and it's already parameterized for us, which is particularly nice. So I want to integrate from a to b the magnitude of the derivative vector dt. All right, so that's the thing that I want to integrate. So I think I'm basically, I'm integrating the velocity to find the distance. That's my goal here. Since it's not a straight line path, I want something that tells me how I move along the path, and that's going to be R prime. So if we go to get that thing, this should be the integral of, try that one more time. The integral, I need to stop being so opaque with my integral signs. I'm going from -1 to 4. So -1 and 4 can get plugged in there and there. Then I'm going to get the square root of a whole mess. I'll just put the top on later because I don't know how long this thing's going to be yet. I need my derivative vector. So let's move this thing out of the way. Maybe make it a little smaller because I'm going to come back to it later. But let's come up here, calculate r prime of t. And what do we get? 2 is the x component. This looks like 2 cosine of 2t for the y component, and -2 sine of 2t for the z component. So keep in mind, derivative of sine is positive cosine, but the derivative of cosine is negative sine. Okay, all that's together. This is 2 squared plus 2 cosine 2t squared plus -2 sine 2t squared. Now I'll put my hat on because I know how long it is. And this is dt. Cool. Well, let's take a look at what shakes out. This will be the integral of, we're still going from -1 to 4. I'm still going to have some square root in here. I'm looking at 4 plus 4 cosine squared 2t plus 4 sine squared 2t. Draw that hat on right there. And then let's take a look at these two pieces. Hopefully I got it all. Yeah. So I've got a 4 cosine squared plus 4 sine squared, where both of those angles are the same angle. Don't want to leave that in the old color. Suppose I should also slap the dt on there. So I'm going to use that trig identity that I had up at the top. Sine squared plus cosine squared is equal to 1. So -1 to 4 times the square root of 4 plus 4 times 1 dt. And now I think we can hopefully see that, there is no dependency on t anymore, so that's just the square root of 8. So this thing is going to be 5 times the square root of 8. Or 10 root 2, if we felt like rationalizing. Also notice that, because that square root came out to not have any dependency on t, in fact, the whole integral had no dependency on t, integrating a constant is just going to end up being the length of the interval. Our length is 5. 4 minus -1 gets us to 5. So green, because it's coming from that -1 and that 4. All right, and I think we're almost, I think at this point we're like basically done. A couple other questions that I tend to come up, so I just want to talk about them in brief. Finding unit vectors, which here we're looking for a unit tangent vector. So unit tangent vector, I've got r prime I get whatever, and I plug something in, then I can get the magnitude of that vector. So notice I put them in blue and in green. And then if I want the unit tangent vector, I just take the blue piece and divide it by the green piece. And as long as you're just going through web work to get all that stuff in, you probably just want to use copy and paste to your advantage here. Or at least that's what I would do. If I got the blue part and the green part right, I would then copy and paste them into the third bar. And all of a sudden, hey, look, I've got my unit tangent vector. A couple of other things, reviewing some quiz questions, just because they may come up again. I know we had a bunch of questions on it. If I want to project my vector onto the I vector, so that's the unit basis vector, the one in the direction of x, that projection shouldn't take any time at all. It's just 3. Right? If I project it onto the I vector, I already have it separated into an I, a j, and a k component. So the projection in the projection in the I direction is just the component on I. Next. Looks like I didn't save myself any space here. Oh yeah, there's one more sort of significant problem I want to look at. Evaluating a cross product. And this is another one that I know everybody super liked. The dot product with J once we're done. We had -1, 3, 5 cross 1, 2, -3. Our resulting vector over here. For I, I've got 3 times -3, which is -9, minus 5 times 2, which is 7. For the middle component, I'm going to have 5 times 1 minus -1 times -3, so 5 minus 3. For my third component, -1 times 2 is -2, minus 1 times 3 is 3. And I'll simplify that mess to get -16 to -5. Blah, 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 blah. Then in the end, I'm taking the dot product of this thing with J. Which is -16 to -5. Oh man, what's up with my angle brackets today? They look awful. Dotted with 0, 1, 0 is the vector J. Really, it means it's only going to pull out the J component. So this thing is 2. Because I just want to pull out this piece. So my answer there is going to be 2. Five times 2 equals 10. Did I do something wonky? Yeah, I sure did. Yeah, so I guess I added 5 and 2 instead of multiplying 5 and 2. Good catch. That should have been, like I said, I'm not very good with numbers. So 5 times 2 is 10. So that's really -19. Not -16. Fortunately, it didn't end up affecting the answer on this one, but still a little embarrassing. Where do you get 0, 1, 0? That is the vector J, like the basis vector J is the vector 0, 1, 0. It is the unit vector in the Y direction. So it's 0i plus 1j plus 0k, if we write it out in terms of the letters. But it is just that unit basis vector in the Y direction. All right, and the last one that I wanted to talk about, I already did out because the work gets a little ugly. And I think if we ask a question like this on the exam, the numbers won't be as bad. but the web work problems were certainly nasty. Problem 11 on homework 4. So I've got two planes, and we're going to find their line of intersection and then the angle between those planes. So I started by finding the normal vectors to both of those planes, which again means, just pick out the coefficients on x, y, and z. And I'm going to end up wanting the cross product of those two normal vectors. What that means is if I take the cross product of their normal vectors, I'm going to get a vector that is perpendicular or orthogonal to both of them. And if I am orthogonal to both of the normal vectors, that means I must be in the plane of both that both those normal vectors are attached to. And in particular, I'm going to run parallel to the line of intersection between those two planes, which is why I'm going to want that. I've got a diagram somewhere that I can probably pull up, but I know it's in the notes on section 12.5. I know someone in the chat was asking, where do we find these notes again? These are in the asynchronous notes on D2L. So if you go to that one page on D2L, click any note section under asynchronous, it'll take you to this document. Or if you navigate back into the folder structure, you can find it at the top of the asynchronous notes and videos. But it's just completed asynchronous notes is the one you're looking for. So I've got myself a normal vector. It came out to 19, 14, 16, bit of an ugly normal vector, but hey, whatever. Or a cross product vector, right? Took the cross product of my normal vectors to get a vector that is parallel to my line of intersection. I'm going to come back to that. But now I have two planes and I need them to intersect with each other. So I have a system of two equations with three unknowns. Anytime I have two equations with three unknowns, that means I get one free choice, one free variable, because I'm currently underdetermined. I don't have enough information to find x, y, and z, but I could have enough information to find just x and y, or just x and z, or just y and z. So I'll pick anything I want to be one of my three variables. Usually it's easiest if you pick one of them to be 0, because that tends to reduce the amount of work that you need to do. And I didn't like the coefficients on z. I was going to have 3 and 5. I don't want to deal with dividing by either one of those numbers. So I'm going to choose z to be 0. Again, I have a free choice because I have a system of two equations with three unknowns. If I just pick z equals 0, then I have a system of two equations with two unknowns. That number matches up, so I can solve for the other two numbers. So I'm going to go through my process. After z is equal to 0, I'm going to solve for x and y. I prefer substitution in order to find all of that. The work here ended up being pretty ugly, so I'm going to skip over the explanation of most of it. It's just some arithmetic that'll get you there, arithmetic and algebra. But I ended up getting 47 over 16 for x and 27 over 8 for y. This is ugly looking. And my choice of 0 for z. But once I do that, I can have my parametric equation for that line, which was the cross product of the normal vectors times t plus that point that I found that's on the line. So ultimately, the equation that I have here is a vector parallel to the line times t plus any point that's anywhere on that line, which is why I get to choose one variable to be a number and then find the other two, because it can be any point that's on the line. There is one nice point somewhere buried in that web work problem, but it's hard to find from the outset if you don't already know what it is, which is why my point came out ugly. Then in the end, what did I want? I wanted the angle of intersection between the planes. That'll be the same as the angle between the two normal vectors. And I have an equation for finding an angle between two vectors. I could use the cross product if I wanted to, but I usually think the dot product method is easier. So I'm going to use the dot product equation, dot product of two vectors, equal the magnitude of the vectors times the cosine of the angle theta. So take their dot product, divide by their magnitudes. I get cosine theta equals some number. Looks like -17 over square root of 1,102. And then theta is just the arc cosine of that number. Cool. So that's it. That's the whole review. So if you're watching the recording, this is Steve Dragoo signing off. Maybe, unless I do one more problem and decide to record again. All right. One more bonus problem. So homework 8, problem 8. We've got a couple of parametric curves. One's expressed as r, one's expressed with t. And we want to find out when they intersect. And then once we know where they intersect, find the angle that they intersect at. So I have taken each of the components, x, y, and z, in those two equations and set them equal to each other. So x is going to be set equal to x with that purple equal sign, yellow equal to yellow, magenta equal to magenta. And then I have a system of 3 equations with only 2 unknowns. And I'm going to run through this thing to figure out when they're going to be equal to each other. So once I have them all set up, solve the easiest one first, plug it into the second easiest, and then save the hardest for last, is my advice to you. Looked to me like the easiest one was going to be the z component. So I solved it first. S is equal to -2 minus t. And then I plugged that into the y component equation because it looked second easiest. Once I did that, I got that t is equal to 1. And once I got a value for t, I plugged it back into the easy equation again to solve for s and got that it was -3. Once I have my t and s values, then I'm going to check them in the final equation. So in the x equation, just to verify that I get the correct answer on both sides. Because if I do get the same answer after plugging them into each of the other things and checking it in the third equation, as long as it comes out to the same thing, that means that the lines do in fact intersect. And if I got some non-equality in the final equation, that would mean that I have 2 skew lines or 2 curves that just do not intersect with each other. Then to find the point, I simply plug those values in for t and for s into R1 and R2 and verify that I get the same point on both sides. Cool, I did. It's at the point -2, 1, 9. So I have my t and s values and my point. So now it's on to that third bit. How do I figure out where these curves intersect? Or how do I find the angle that these curves intersect at? And the way to do that is to find some parallel vectors at the point of parallel vectors. Find some tangent vectors at the point of intersection. And then find the angle between those tangent vectors. That seems like the easiest way, which means I'm going to end up wanting R1 prime and R2 prime. So let's go get those things. R1 prime of t is going to be the vector 3 minus 10t, 2, -1. And R2 prime of s is going to be the vector, what is that, 6s, 3, 1. Cool, I've got my 2 derivative vectors. And now I'm going to use copy and paste to be my friend. Move down here, paste it where I've got some space to work. And I want to plug in my t and my s value at the point where they intersect. Oh, crap. All right, so R1 of 1 is -7 to -1. R2 at -3, because that was my S value, is -18, 3, 1. And now I want cosine of theta. Well, really, I want theta, but this means I'm going to take an inverse cosine at the end of all this mess. That should be the dot product divided by the magnitudes, right? So R1 dot R2 divided by magnitude R1, magnitude R2. So I'm being a little fast and loose with my notation here. I want R1 and R2 with 1 and -3 plugged in, but it's just quicker to write it down this way. Take my dot products. Oh, this is going to be ugly, isn't it? 7 times 18, 70 plus 56, 126, I think. Plus 6 minus 1 divided by the magnitudes of those two vectors. 49 plus 4 plus 1 is 53. And oh boy, 18 squared plus 9 plus 1. So I'll just have to add 10 to whatever 18 squared is, which 289 I know is 17 squared. 400 minus 40 is 360. 361, I think. Nope, that's 19 squared. What is 18 squared? Anybody got it in the chat? Thank you, chat. 324. So if 18 squared is 324, I want to add 10 to that. So 334. So then theta is just going to be the arc cosine of that mess. Arc cosine of 132, so 131 after I subtract 1, divided by, I'm just going to call that the square root of 53 times the square root of 334. I can plug all that into my calculator. Whatever I get there should be my angle. We probably want it in radians. Root 54. Oh, crap, you're right. That is root 54. I, once again, am not very good with numbers. So let's just rewrite that whole denominator. Square root of 54 times 334. Cool. Yeah, good catch. Thanks. All right, and that's the end of bonus problem 1. All right, so bonus problem number 2. Let's get another arc length into the mix. So if we're getting arc length, we're going to want a derivative vector, which on this one looks like it's going to be, let's throw some color in there, 0, 4t, and, oh, it's derivative of t cubed, 3t squared. Wow, I'm having a day of it, it seems. Try this one more time. 3t squared. Yeah, it has apparently been a long day if I can't even get that derivative. Oh man. I always say I'm not very good with numbers, but I thought I was at least good at math. Oh boy. All right. Oh boy. Integral from a to b of the magnitude of r prime. Oh boy. I forgot my hat over here. R prime of t dt. In our case, we're integrating from 0 to 2, because that's what we're told over here, times the magnitude of r prime. So again, I'm going to wait on the hat to my square root because it's going to get ugly before it gets pretty. 0 squared plus 4t squared plus 3t, nope, 3t squared, and then squared again. All right, put the hat on, dt, put the hat, the roof. I don't know, I've probably heard it both ways. Let's see what we get. I'm looking at an integral, again, from 0 to 2 of something. 16t squared plus 9t to the 4th power. Again, throw our hat back on, get a dt in there, and let's see what shakes out. Uh, 0 to 2. I've been doing this so long, my hand's not steady anymore. Okay. There we go. We got ourselves a square root. And we've got some square numbers on the inside of that square root. So I'm going to factor out a t squared. And it should leave me with a 16 plus 9t squared dt. Oh, close that parenthesis. This thing then, since I now have a square number, that t squared, I am just going to factor that right on out. 0 to 2, pull out that t, highlighted it there in blue so we can kind of track its progress throughout the problem. Well, this is 16 plus 9t squared dt. And if you're remembering your u substitution from Calc 2, you might be seeing what it is we're going to want to do right here. U substitution. What color have I not used yet? I haven't used red. So u is going to be 16 plus 9t squared, everything that's on the inside of that unit circle, or unit circle. I am tired. Everything that's on the inside of that square root, 16 plus 9t squared. And then we're going to want to get du, which is going to be, what is that? 18t dt, which means that if I have t dt, that thing is going to be equal to 1 over 18 du. Notice I highlighted that t in blue because it's going to show up nicely back in our integral. So, or back in our integrand. That's the thing that's on the inside of the integral, if memory serves. So that means I've got a bunch of stuff to do over here. I'm just going to write my generic integral sign for a second here. I've got the square root of u, because that's how I set it up. On the outside, I have t dt, so that's du, and also a 1 over 18 that goes here. Now, the way the textbook explains how to do it, you're supposed to find new bounds for u. I've never liked doing that, so I'm going to skip that step. And we're just going to come back to 0 and 2 at the end. Because now if we integrate this thing, it's not so bad. U, square root of u, that's u to the 1/2. It's going to integrate to u to the 3/2 times 2/3. So we'll have 2/3 times 1 over 18 times u to the 3/2. Right, so I'm just going to put some parentheses here, 3/2, where u is supposed to go in here. Now that I've done my integral, but I'm going to substitute back in to have a 16 plus 9t squared, because that's what we know u to be. And since I substituted back to t, that means that my bounds for t still work. So I always prefer to substitute back in when I'm done and then use my original bounds rather than solving for new bounds. I think that's just like, it's usually more effort than it's worth. Plus that way, I had some nice looking numbers to begin with, so I'll just keep using them. So now we get the extra joy of actually evaluating all of this stuff. So let's see what we get. 2/3 times 1/18. I'm pretty sure that's 1/27. Simplify that a bit. Times. What do we get when we plug in 2 for t? 9 times 4. 36 plus 16. You know what? Let's just call that 16 plus 9 times 4 minus 16 plus 0. That one's easier to do. Don't forget that these things are all still to the 3/2 power. So we'll add that thing back in. Yeah. That's going to look ugly. 36 and 16. Is that like what, 40? No, 52? Yeah, there's no square rooting that. Let's leave it there. You'll get a number. You can plug it into your calculator, but it's not going to simplify any nicer than that. So that concludes bonus question number 2.